The Bluetooth device is ready to pair.
Hello Philippines, hello world, hello other parts of the world. Welcome back to my YT channel. This is again, I am a singer, eternal voice. Okay, so we will show to you different problems for free energy computation, or the change of free energy for the vaporization of water. Okay, we have this like this. Hello guys. So consider the following enthalpy and entropy data for water in the both the liquid gaseous state. So we have the table of H2 liquid and H2 gas. So we have two columns in the table: the delta heat or enthalpy of formation in terms of kilojoules per mole. We have water, which is equal to negative 286.83. This is the delta heat flow. So the second column for each two liquid, we have the change or the entropy formation is 70 joules per mole Kelvin. And then we have the H2 gas state. We have delta H, which is equal to negative 241.82, and the delta S is equals to 188.2. Okay, like that. Okay. Okay. The question will be, what is the free energy change for the vaporization of water at room temperature? We have the given here. It's very clear. The delta H of formation, the change of enthalpy formation. Okay, like that. So our clue here is the evaporation process or the vaporization process, in which this is a process that liquid changes to the vapor state. Okay, so only the phase changes. Actually, this is not chemical reaction. This is only phase changes. But still, we will apply the free energy change for this. Okay? So in the second law of thermodynamics, we have this formula for, okay, it doesn't mean only to put Gibbs, okay, but it's also the same with change in free energy. It's just equal to Gibbs free energy, delta G. Okay, delta G is equal to delta H, change in enthalpy, minus the temperature times delta change in entropy, or delta S. T is the temperature in terms of Kelvin. Okay, so what is being asked is to calculate the free energy change. Okay, so let me use this formula. Okay, since our delta H formation have, what's the name of this one? A circle at the top. So that is standard, right? Here. Circle at the top of the delta H and circle, small circle at the top of entropy, that's the standard. So delta change in entropy standard, delta change in enthalpy standard. So we need to compute first the change of free energy standard, which is delta G, okay, standard RxN, or reaction. Okay, so we have now that here. Okay, like this. Okay. So the delta H, or the delta change in enthalpy, is just equal to the delta change in enthalpy formation standard reaction. So we can say delta H formation standard in the liquid state, or shall we say gas state first, because it should be product first. Okay, so again, delta H formation standard in the reaction is equal to the summation of the number of moles in the product, which is in the gas state of H2O gas. Okay, times the delta H formation of the H2O gas also, minus the summation of the number of moles of H2O liquid times the delta H formation standard of H2O liquid. So from liquid state to vapor state, so evaporation process, right? Or vaporization process. This is not a chemical reaction. Okay? Like that. So we will use this one, and then we have the given, and then we have to substitute one by one already. Okay, so here in our reaction, H2O liquid turns to H2O gas in the vapor state. So the number of moles of H2O liquid and H2O gas is just the same. One atom of H2O molecule and one atom of H2O in the gas state also. Okay, or we can simply say 1 mole of hydrogen gas. Oh no, 1 mole of oxygen, 1 mole of oxygen, and 2 moles of oxygen. Something like that. Okay, so or we can simply say 1 mole of H2O or 1 mole of H2O, something like that. Okay, okay. So we can compute now. So in this reaction, so delta N, substitute the number of moles of H2O gas first. So we have 1, right? Because liquid water, 1 mole of liquid water equal to 1 mole of gaseous water. So in reversible reaction, like this, the arrows, 2 arrows represent. Okay, so substitute now. So let's have this. Okay, 1 mole of H2O gas. Okay, like that, times delta H of formation of H2O gas is negative 241.82 kilojoules per mole, like this. Okay. Minus the number of moles of H2O liquid, which is 1 mole, times the delta H of formation of H2O liquid, so negative 286.83 kilojoules per mole. Okay, so this is gonna be the substituting of values. Okay. Delta H of formation in the reaction. So we substitute the respective number of moles of the H2 liquid and H2 gas, which is equivalent only to 1. Okay, and we have the value of delta H formation. So just substitute. Okay, and then you need to do the basic math for this. Okay, 1 mole. Okay, 1 times 2 is equal to negative 241. This is only 1, right? So negative 241.82, okay, minus negative 286.83. Okay, so it will become plus here. Okay, so 241.82 plus 286.83 is equals to 528.65. Okay, again, 241.82 negative 241.82 plus 286.83 is equals to 45.01. So our delta H in the reaction formation is equals to 45.01. Okay, the mole will be cancelled here, class Ha. The mole will be cancelled to the delta H formation, which is kilojoules per mole. So what will left is the kilojoules only. So kilojoules ni siya. 45.01 kilojoules. If you try to convert that in joules, let's multiply that to 1,000, right? Kilojoules. Okay? Let's multiply that by 1,000. Okay? So we can say 1, 2, 3. That is 45,000.010. Right? Okay, so 45.01 times 1,000. 45,010 na. 45,000 joules. So which you will use? It could be kilojoules or joules. It depends. Okay, in the choices of the question in the examination, whether it is joules or kilojoules. Okay, now we are not yet done. We need to solve also for the entropy of formation. Okay. Entropy, the same story. Okay, delta change in entropy formation of the reaction is equals to the summation also of number of moles of H2 gas like this, and the entropy of formation of H2 gas, which is given here, like 70. Okay, this is 70. The unit is different, huh? This is joules mole Kelvin shot. So 70 joules mole Kelvin. Okay, like this, and then times the temperature, which is mentioned here as 298. Okay, 298. Okay, or it's mentioned in the question, what is the free energy change of the vaporization of water at room temperature? So room temperature class, take note that is 25 degrees Celsius. Sometimes it will never be mentioned in the problem. It will just say room temperature, but automatically that room temperature is technically equal to 25 degrees Celsius, and you have to add that with 273 Kelvin. So that will become Kelvin. So I will multiply this entropy of H2O gas with 298 Kelvin. Okay, 298 Kelvin. So cancel ang Kelvin. Then multiply po niya siya sa 1 mole of H2O gas. Para makancel ang mole. So, ang habilin is joules na lang siya. Okay. This is only for H2O gas minus H2O liquid. So, the number of moles minus, okay, times the entropy of H2O liquid. Okay. Entropy of H2O liquid, which is in the table here represented as 188.8. It's here. So tayo, no? Sa pagpakita sa kuan, papel ramon board, wala whiteboard. So 188.8. Okay, times, very hard to discuss. 188.8 joules mole Kelvin. Again, times 298. Okay? So cancel, 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 cancel. So what will left is joules. Like this. Okay. So we need to subtract this two. So 70 times, okay, because this is sorry, this is a gas first. It's reverse, right? It's gas first. Okay. So this is reverse actually. Sorry, it's reverse. That is gas minus liquid. Because product minus reactant man siya. Okay. So just reverse this one, it would be okay. In a way, the A is equals to 56024, this one. So 56024 minus 298 times 70, 2860. So this is 56024 minus 2860. So this is 35164. So our entropy will be 35164. Then cancel naman sa mo. Joules na lang sa siya. So joules. Okay. So class, we have an delta H formation of the reaction, which is 45010 joules. And we have the delta change entropy standard of the reaction is 35164. Now we use this formula now here. Okay, here in the second law of thermodynamics, this one. Use this one. Delta G is equals to delta H minus T times delta S. So we substitute this value here. So delta H is equals to 45010, right? So 45010 joules siya minus, okay, entropy is 35164. Entropy, okay. So we have, since kanina class is joules naman siya, i-convert naman na to daan. We converted it already by employing the temperature. So no need to multiply the temperature here, in here. Okay? No need to multiply here. Subtract the value directly because we included the temperature already in the individual computation. So this is minus 164 joules. So it could be on the other way around. You have to compute first the temperature. But what I did at first, I computed both the temperature and the entropy so that the answer will be deducted here automatically. So it depends on you what you're going to do. You do it first without temperature or just later temperature here. It's just the same. As long as your entropy is in joules and your enthalpy is joules, then it will be deducted by having the same unit. Okay? Something like that. So 45010, 45010 minus 35164. So I have 9846 joules. So my delta G now is 9846 joules. This one. The 9,000, okay, 846 joules. It is a positive value. So therefore, this is non-spontaneous. Okay, because positive value of delta G is non-spontaneous. Something like that, okay? So in this case, this is not a reversible reaction. Okay, say because this one I assume to be reversible reaction one in the first place. I believe that water is just equal to water, and then it will go back to water also, but it's not. Because let's analyze, because it's already vapor or the gas. It's impossible for the vapor or the gas to come back to water. Okay, we analyze already. Okay, say, for example, that is a liquid, it turns to vapor. The vapor will not go back to liquid because it's already dissipated into the atmosphere or lost into the atmosphere. So it never goes back to liquid. So this is non-spontaneous or irreversible reaction. So my first analysis is wrong because I computed by the answer with this delta G. So the theory Okay, so it's not reversible. Okay, it's irreversible. Okay? I believe water is just equal to water vapor shock, but actually it's not because the phase changes matter. So we have to analyze also. Okay, so I saw really on the spot, that's why. Okay, so that's it. Very easy, right? If you assume at first, then you can change your first assumption. If you have the final solution and the final answer, then you can change your first assumption or first hypothesis. This is gonna be a first hypothesis because you are not really sure, right? Okay, sometimes here because of the delta G, we found out that is 9,846. So this is non-spontaneous input shock. So non-spontaneous is increasing the irreversibility of the process. Okay, so that's non-spontaneous delta G. In the first place, if it's reversible reaction, then the delta G is already equal to zero by means of theory. So actually, this is not a reversible reaction. Okay? So thank you so much. If you like this live streaming, short live streaming, then you can comment down below in the comment section, and you can subscribe my YT channel if you want to, or you can even share it to anybody else if you want to also, and then you can click the notification bell for some newest updates. I am Singer, Eternal Voice. Bye bye. God bless everybody. See you later. Okay.